All right, welcome. Today, we're going to pull back the curtain on the invisible world that powers literally everything around us. I'm talking about our phones, our lights, you name it. We're getting into the fundamental rules of electricity, and trust me, they're way simpler than you might think. So here's a weird question for you, right? What could a massive, chaotic bolt of lightning possibly have in common with this super precise gadget in your pocket? Well, the truth is, they're both playing by the exact same elegant set of rules. And today, we're going to figure out exactly what those rules are. So to get started, you got to meet the three main characters in this whole story. I like to call them the electric trinity: voltage, current, and resistance. If you can get a handle on these three, you've pretty much got the key to understanding everything else. First up, we've got voltage. Now, the simplest way to think about voltage is that it's the push. It's the force, kind of like an electrical pressure that gets all the electrons moving in the first place. Without voltage, nothing happens. It is the get up and go of any circuit. And to make this super clear, let's use an analogy we can all picture. Think about water flowing through a pipe. In this whole scenario, voltage is the water pressure. The more pressure you have, the more force there is pushing that water along. Simple, right? Next up in our trinity is current. So if voltage is the push, then current is the actual flow. It's all about how many electrons are actually zipping past a certain point in the circuit over a set amount of time. And if we go back to our water pipe, current is the flow rate. So it's not about how hard the water's being pushed, but how much water's actually moving through the pipe. Is it just a little trickle, or is it a raging torrent? That's current. And our final character is resistance. Now, just like the name says, resistance is what pushes back. It opposes the flow of current. Every single material has some level of resistance. It's like electrical friction that slows things down. And as we're about to see, we can actually use it to get useful work done. So in our pipe analogy, resistance is anything that gets in the way of the water flow. Imagine pinching the hose or trying to force all that water through a much narrower section of pipe. That creates friction, it slows down the flow, and that, right there, is resistance in action. Okay, so we've met our three key players: the push, the flow, and the friction. But here's the thing. They don't just exist on their own. They're all tied together by one single, incredibly powerful, and absolutely unbreakable rule. And this is the million-dollar question, isn't it? How do these three different forces actually relate to one another? Like, if you crank up the push, what happens to the flow? And if you add more friction, how does that change everything? Well, luckily for us, one brilliant physicist figured it all out. That physicist was George Ohm, and his discovery is just beautiful in its simplicity. All it says is that more push, so more voltage, means you get more flow, or current. But more friction, more resistance, means you get less flow. See? It's this really elegant and totally intuitive relationship that became the absolute bedrock of electrical engineering. And here it is in all its glory. Ohm's law. V equals I times R. Voltage equals current times resistance. This little equation is honestly one of the most important in all of physics. It's the key that lets us design and analyze pretty much every circuit, the unbreakable rule connecting the push, the flow, and the friction. And check this out, this is a super handy tool called the Ohm's Law triangle. It's a fantastic little trick for remembering the formula. All you do is cover up the thing you're looking for, and the triangle just shows you the equation you need. It's simple, but man, is it effective. Okay, so we've got the push, the flow, and the friction all working in harmony. But so what? I mean, why do we even build circuits in the first place? Well, the answer is to get work done. And in the world of electricity, that work is called power. Power is really just the rate at which energy gets used or converted. So when your light bulb is glowing, that's power turning electrical energy into light and heat. When a motor spins, that's power turning electricity into motion. It's the whole point, the end result, and it's measured in a unit I know you've heard of: watts. And hey, just like Ohm's law, power has its own simple formula and its own handy triangle to help you remember it. The main idea here is that power equals voltage times current. This triangle just shows how the push and the flow combine to figure out how much work is actually being done. And of course, you can use it to solve for voltage or current too. All right, theory's great and all, but let's make this stuff real. Let's jump into a practical example and see how we can use these rules to analyze a real circuit and find the missing piece of the puzzle. So here's our setup. We've got a circuit with a 12-volt power source. That's our push. And it's connected to something with 6 ohms of resistance. That's our friction. So the big question is, what's the flow? How much current is actually moving through this thing? Well, to figure this out, we just follow the steps. We know our voltage is 12 and our resistance is 6. We look at our handy Ohm's law triangle and see that to find current, we need to divide voltage by resistance. So we just plug in the numbers, 12 volts divided by 6 ohms. And bam, there's our answer. The flow of current in this circuit is 2 amps. See? With just one simple rule, we can take the things we know and figure out exactly what we don't. It's seriously that powerful. So, okay, we solved one little problem. But why does any of this really, truly matter? Well, because this isn't just about some tiny circuit. These exact same rules are the foundation of all modern technology. And this is what's just so incredible to me. The same principles we just used scale up perfectly. I mean, from figuring out the current for a single little LED to designing the complex microchips inside your smartphone, all the way up to managing the entire global power grid. It all comes back to V, I, and R. So let's lock in these key takeaways. Voltage is the push, current is the flow, resistance is the friction. And Ohm's law, V equals I times R, is that unbreakable rule that ties them all together. These simple concepts are truly, honestly, the bedrock of our entire modern world. And that kind of leaves us with a final thought, doesn't it? We just saw how one simple, elegant rule that was discovered almost 200 years ago laid the foundation for our entire technological age. It really makes you wonder, what's the next simple discovery, the next unbreakable rule that's just waiting out there to be found, and that's going to change our world all over again? Thanks for tuning in.